Across the vast frozen lands of Siberia, a region covering millions of square kilometers where temperatures can drop below -50 degrees Celsius, Russian engineers built a massive oil pipeline stretching thousands of kilometers to transport crude oil directly to China. Millions of tons of steel, tens of thousands of heavy machines, and tens of billions of dollars in investment were mobilized to transform the wild taiga forest into a transcontinental energy highway. But how do engineers actually build an oil pipeline on this scale in some of the harshest conditions on Earth? Let's explore the full process with Mandarin Tech. The oil pipeline connecting Russia and China is part of the Eastern Siberia Pacific Ocean pipeline system, a major energy corridor about 4,700 kilometers long that stretches from oil fields in Eastern Siberia to the Pacific coast, with an important branch running directly from Skоворodno to Deqing in China. This branch has been operating since 2011, with a transport capacity of around 30 million tons of oil per year, making it one of the largest overland energy supply routes between the two countries. Built across the remote taiga forest, regions of permafrost, and areas with almost no existing infrastructure, the project transforms Siberia into a strategic energy corridor that directly connects two of Asia's largest economies. The very first step of the project began with a global-scale material selection process for the pipeline itself. More than 100 steel pipe samples from some of the world's leading manufacturers were tested to identify which components could withstand the extreme conditions along this energy corridor. After multiple rounds of rigorous evaluation, only the Azura pipe plant met the technical requirements and was selected as the main contractor to manufacture 1,000 kilometers of pipeline for the project. The project required thousands of massive steel pipe sections, each measuring about 12 meters in length, weighing nearly 9 tons, with a diameter of 81 centimeters and a wall thickness of up to 39 millimeters. These were not ordinary pipe segments. They were high-performance engineered components designed to withstand temperatures as low as -50 degrees Celsius. To manufacture oil pipelines, it is necessary to use a type of steel that has both very high strength and sufficient ductility at the same time. During the slab casting process for the future pipe sections, special attention is given to controlling the chemical composition and the microstructure of the steel. After that, in furnaces operating at temperatures above 1,000 degrees Celsius, the steel is heat-treated, and then rolling mills press the slab billets into steel plates with precise dimensions for the future pipe sections. Now the steel plates are moved to the forming stage. The plates are bent using a 12-step high-capacity press, or formed in 2 consecutive stages, first with a U-press and then with an O-press. The use of these multi-step forming methods helps ensure that the steel plates are accurately shaped into a complete round pipe form. The next stage is 3-layer vacuum welding. The longitudinal weld along the pipe body, both on the outside and the inside, is carried out entirely using specialized automated equipment. This system prevents air from entering the welding area, ensuring the joint achieves the highest level of tightness and strength. After that, the weld quality is inspected using ultrasonic testing and hydrostatic testing. Both the pipe body and the weld must withstand pressures of over 420 atmospheres, which is about 1.5 times higher than the maximum expected operating pressure of the future pipeline. At this stage, the product is almost ready for transportation. All that remains is the application of a polymer insulation coating. The composition of this insulation layer was specially developed for this offshore gas pipeline. At this stage, the pipes also undergo heat treatment, which helps increase their strength and their ability to withstand large temperature variations along the entire length of the pipeline. The finished pipe sections are transported directly from the manufacturing plants to staging yards along the construction corridor across Russian territory, and are then distributed to individual installation sites along the Trans-Siberian pipeline route toward China. There, the pipe sections are continuously welded together in the field and lowered into pre-excavated trenches, gradually forming a transcontinental oil pipeline thousands of kilometers long. When the branch pipeline directly connecting China as part of the Eastern Siberia Pacific Ocean (ESPO) system When into operation, it became capable of transporting about 30 million tons of crude oil per year. In the Ussuri taiga forest, the first outlines of a massive energy project are gradually taking shape. Construction teams are simultaneously building two large diameter pipelines, a main oil pipeline and a parallel energy pipeline, stretching for about 230 kilometers, running almost within the same technical corridor. Alongside the main route, the next phase of the Eastern Siberia Pacific Ocean pipeline system is also being built, connecting the Skovorodino pumping station to the oil export port on the Pacific coast. Leading the construction effort are teams of logging workers and bulldozer operators, who are preparing the ground for the main works. The pipeline corridor is being cleared with high precision, exactly following the design width of the project. And right at the edge of this cleared strip begins a stretch of primary forest that has remained almost untouched. Before becoming part of the pipeline route, each steel pipe section must go through a careful preparation and inspection process. To speed up construction, some pipe sections are pre-welded into longer strings at field assembly yards. Before welding, the pipe ends are machined precisely using specialized equipment. These modern welding systems allow for high construction speed while still ensuring stable weld quality. With just one such production line, more than 100 weld joints between pipe sections can be completed in a single day. However, in areas with complex terrain and difficult access, where automated equipment cannot be used, construction teams switch to semi-automatic welding methods. In these cases, each layer of metal is welded carefully in multiple steps to ensure that the pipe sections remain strong and leak tight before being placed onto the main pipeline route. Steel pipe sections tens of meters long are lifted in coordination by specialized cranes, then lowered into the pre-prepared trenches with accuracy measured in centimeters. Once the pipe sections are precisely aligned along the pipeline axis, they are quickly welded together continuously to form a steel energy corridor stretching across the taiga forest. Today, pipeline construction teams work much faster than the pioneer workers of the former Soviet era. Technology has changed significantly, and with modern automatic welding methods, each joint between two pipe sections now takes no more than 15 minutes to complete. In the past, completing a weld like this usually took 3 to 4 hours. The welded joints along the pipeline section are inspected using self-propelled X-ray inspection equipment. If any defects that do not meet the required standards are detected, the joints are repaired immediately on site. Once the joints pass inspection, the construction teams proceed to apply protective coating to the pipe section. To protect the pipeline from rocky ground conditions, the outer surface of the pipe is wrapped with an additional protective layer known as a rock shield coating. The project specialists had to work in harsh and sometimes nearly extreme climate conditions. In spring, construction teams faced dense swarms of insects, and in summer they were replaced by horseflies and biting flies. In the forests of this region, tsetse flies can even be found. The weather in the primary region is also highly unpredictable. The humid, swampy heat is sometimes suddenly replaced by heavy, almost tropical rainstorms. After such rains, the ground becomes not only slippery underfoot, but so muddy that it can seem to flow beneath the wheels of off-road vehicles. The Sakhalin, Khabarovsk, Vladivostok main gas pipeline passes through an area with very complex terrain. The route includes hills up to 300 meters high, many rivers, as well as swampy areas and hard rock ground. Thanks to the use of modern technological systems, construction teams were able to overcome all obstacles along the route. Their experience and equipment allowed them to build this main pipeline in a relatively short time. On rocky sections of the terrain, construction teams could complete about 500 meters of pipeline per day. In flat areas, the construction speed could reach up to 2 kilometers per day. Following the pipeline route, the construction workers' camps also move continuously along the construction corridor. They can be found in many different regions across Russia, as the teams are involved in some of the largest energy pipeline projects in Eastern Siberia and the Far East. Engineers and workers are currently building key sections of the Eastern Siberia Pacific Ocean oil pipeline, a system that will connect oil fields in Eastern Siberia with an export port on the Pacific coast and a branch line running directly to China. In addition to the overland oil pipelines connecting Russia with China, Russia has also developed a similar large-scale offshore project called Nord Stream, a pipeline laid along the bottom of the Baltic Sea to transport natural gas directly from Russia to European countries. Before Nord Stream 2 could become an offshore construction project, it existed first as a complex planning challenge that stretched on for many years. The objective was to create a direct connection between Russia's massive gas fields and Europe's major energy markets. However, the shortest line on a map was not necessarily the most feasible route on the seabed. Spanning roughly 130 kilometers, the proposed pipeline would pass through the territorial waters or exclusive economic zones of 5 different countries, each with its own environmental regulations, technical standards, and strategic interests tied to the Baltic Sea. From the earliest stages, the marine environment became a central factor shaping the entire planning process. The Baltic Sea is a semi-enclosed body of water with limited natural self-cleansing capacity and a long history of pollution from industrial activity, shipping, and coastal cities. Even minor disturbances to the seabed can resuspend contaminated sediments or disrupt sensitive ecosystems. For this reason, every country along the route required detailed environmental impact assessments before granting construction permits. To meet these requirements, survey teams carried out high-resolution mapping of the seafloor. Multi-beam sonar systems, seismic instruments, and unmanned underwater vehicles were used to analyze seabed topography, sediment layers, and potential risk zones. One unique challenge in the Baltic Sea is the presence of unexploded munitions left behind from World War I and World War II, scattered across the seafloor for decades. Whenever possible, the pipeline route was adjusted to avoid these hazards. In areas where avoidance was not feasible, the unexploded ordnance had to be neutralized through controlled detonations. To reduce the impact of underwater shock waves, contractors deployed bubble curtains around the blast sites, helping absorb acoustic energy and protect marine life. Only after the route was finalized, environmental risks were brought under control, and the legal requirements of each country were satisfied could Nord Stream 2 move into the construction phase. In many ways, this planning stage became the foundation that determined the success or failure of the entire project. After fabrication and concrete weight coating were completed, the steel pipe sections entered the transportation stage to coastal ports. This was a critical logistical phase, requiring precise coordination between manufacturing plants, storage yards, and port infrastructure. Each pipe section, weighing several tens of tons, was loaded onto specialized transport vehicles, or inland vessels, and moved to coastal transshipment ports in Finland and Germany. At the ports, the pipes were staged in large storage yards and arranged according to the planned installation sequence to optimize material flow. Heavy-duty cranes and handling systems were used to load, unload, and position the pipes safely, minimizing mechanical impact and the risk of damage. From these port facilities, the pipe sections were gradually transferred onto supply vessels or directly onto offshore pipelaying ships, following carefully planned schedules that ensured a steady and uninterrupted supply of materials to ongoing offshore operations in the Baltic Sea. On the specialized pipelaying vessels operating in the Baltic Sea, the entire deck is organized as a closed-loop industrial production line, where each installation step is carried out continuously in the middle of the ocean. The process begins when 2 pipe sections, each weighing up to approximately 24 tons, are positioned for welding and precisely aligned. Automated welding systems then complete the circumferential weld around the pipe, after which specialized inspection equipment immediately scans the entire weld to detect any structural defects or leaks. Only joints that meet all technical standards are allowed to proceed further along the line. Next, the welded joint is sealed with a dedicated protective system, combining heat shrink sleeves and elastic filler materials to prevent corrosion, while providing the flexibility needed for the pipeline to adapt to uneven seabed terrain. As the vessel slowly advances along the predefined route, the connected pipe sections are continuously guided into the water and gradually lowered into their designed position. Through tight coordination between transportation, installation, and positioning systems, this method enables the installation of up to 3 kilometers of pipeline per day, a pace rarely achieved in offshore construction. The pipeline installation process had to address geological and marine environmental challenges through seabed preparation and the management of crossings. While in many areas the seabed was smooth enough to keep the pipeline stable with minimal intervention, this condition did not apply along the entire route. In sections with uneven or rough seabed terrain, Specialized vessels were deployed ahead of pipe installation to level depressions using rock and gravel, creating a flat and stable foundation for the pipeline to rest on. By contrast, in shallow water areas where pipelines are exposed to strong wave action and hydrodynamic currents, the pipes could not be laid directly on the seabed. Instead, they were placed inside pre-excavated trenches, which were later backfilled to secure the pipeline in position. In addition to natural seabed conditions, the Nord Stream 2 route intersected with other existing subsea infrastructure. At locations where the pipeline crossed underwater power cables, telecommunications cables, or other pipelines, rock berms were installed to protect each utility at these crossing points. These protective measures ensured the structural integrity and long-term reliability of both systems sharing the seabed. So now you've explored the entire construction journey of Russia's massive pipeline system, one of the largest overland energy corridors in Eurasia today. Thank you for staying with Mandarin Tech until the very last moments of this video. Stay with us in the next episodes as we continue exploring more amazing engineering projects around the world.